Makhdoumi, who comes from Duke University.
Thank you so much. Thanks. Special thanks to the organizers for having me at Simons and in this workshop. So this has been an amazing experience for me. So I've learned so many things over the last few weeks, and I'm sure this will continue to be the case. So today I'm going to talk about testing voluntary social distancing in the spread of infection, and this is a joint work with Daron Asamoglu, Asu Ozdagdar, and Azarash Malikian, who is sitting here in the audience. So one thing I should highlight is we sort of thought about this work at the very early sort of stages of the pandemic, and back then testing was one of the main issues. So with sort of that mindset, let me tell you what this work is about. So testing is one of the most sort of effective ways for controlling pandemic. I can list many reasons for why that's the case. I mean, for instance, it helps to identify infected people and so that they can treat faster. It helps to again identify and isolate infected people so that you prevent the spread of the virus, and it also helps to identify people who came into sort of close contact with positive cases so that they can take the sort of necessary precautionary actions, and this is going to reduce the sort of asymptomatic transmissions. And there's no doubt that because of these reasons, many government agencies have invested a lot in sort of expanding the testing capacity. So obviously absent the sort of strategic behavior of users, which hopefully I'm going to clarify this term throughout the talk, increasing testing is going to sort of decrease the infection in a society. So it's going to make users better off. So the sort of question we're going to ask in this talk is, is there a downside to increasing testing? And the sort of logic that we have in mind is, by increasing testing, individuals are going to become sort of less cautious. They're going to be more socially active. And this can potentially increase the sort of the infection in the population, and potentially this can offset the impact of increasing testing. So this is the sort of trade-off we're going to explore in this talk. Yes.
When you say testing, do you mean large-scale screening of the whole population, or do you mean like targeted testing if you have symptoms, or what?
Yeah, very good question. No, so this is like a very simple. I will talk about the model. So the question was, what do I mean by testing? Is it like a targeted testing? So it's not. So it will be, I have a society, and then with some probability, I'm going to test each one of the individuals in that society, in a homogeneous way. So I'm not doing any targeted testing or any contact tracing or anything like that. So this is like a very simple theoretical modeling framework, and by testing I mean you allocate these many tests to this community. So with this probability, you're going to test each one of these people.
Well, then I would maybe not agree with you that it's shown to be effective. If you do large-scale screening, you have to screen huge amount of people very frequently to have any effect.
Very good. Yes, I see your point. So what we're going to see is, from this point of view, that by increasing testing, people are going to be more socially active. So from that perspective, it's going to hurt as well. But you're right that if I have this amount of tests, there may be better ways for sort of targeting these tests to individuals in society. I completely agree with that. Yes.
Can you clarify a little bit more on why people will increase their level of social activity?
Very good. So the question was, why people are. So the question is why people are going to increase their social activity level. And so this is going to be clear once I introduce the model. But as a sort of a precursor, it's like when there are more tests out there, you feel sort of more comfortable to go out. It just increase your social activity because you're just more confident that if there are positive cases out there, with a higher probability it's going to be caught. So you just increase your social activity. So that's the sort of logic.
So, and you also assume if someone is detected as positive, they will behave the right way. Like
yes, exactly. So
okay.
yes, so once I introduce the model, it's going to become clear. But once you test positive, you're going to be isolated. Yes, so you're not going to spread infection anymore. Yes, which may not necessarily be the case, but again, this is more like a modeling framework, and that's an assumption we're going to make. And besides testing, another instrument to control pandemic is social distancing, and there evidence that animals do that to some extent. So there may be some evolutionary reasons for doing that. So the other question we're going to sort of explore in this talk is how should testing be combined with social distancing? So that's sort of the second question we're going to explore in this talk. So with that in mind, so let me tell you, the plan for this talk. So we're going to develop a game theoretic model to study these issues. So this is, again, more like a modeling framework. So there is no data. We're going to model social activity and voluntary social distancing as a network formation game. So this is going to be a network formation game. So what do I mean by that? So individuals are going to decide about their social activity levels, which is going to sort of determine a contact network, an underlying sort of social network over which the infection is going to spread. And then, how do we, sort of think about the spread of the infection? So I'm going to use a sort of very simple discrete time process to sort of model the spread of the infection. So I'm not going to use, SIR type of models. And this choice is mainly for tractability. Hopefully this point will become more clear throughout the talk. So what does testing do in this framework? So testing is going to enable isolation of the infected individuals. Once I test someone, I'm going to assume that I'm going to end up isolating that person. So there's no infection spreading from that infected person. And then what do we show with this framework? So I'm going to characterize the equilibrium of this game, which is basically the activity level of individuals for any sort of given testing policy. And then
how much do your participants know about the state of the world? Do they know the global level of infection? Do they know their probability? Do they know which of their friends are infected, who got tested? Or so what information do I as a player in this game have?
So this is going to be like a full information game. So I know the activity level of other people. So I know, people are going out with this rate.
So I know if you're going out, I know it for every one of my neighbors.
Correct. And then like the testing probability that is out there as well.
And I know that you got tested.
Yes, I got tested as well. Yes, that's right.
But I don't see you sneezing, so I don't know whether you're sick.
Well, so that's not going to be important because you're going to make that decision. So in the morning you're going to wake up, you're going to decide whether you're going to go shopping or not. At that point, whether the person you're going to interact with is going to be sneezing or not, it's not going to matter. So, you sort of ex ante decide whether you want to go out or not. And then once we sort of characterize the equilibrium, we're going to look at the optimal testing policy and then sort of characterize the impact of the testing policy on the equilibrium outcome. Yes, please.
Is there a pre-existing social network prior to this contact network form?
Very good. No. So, it's just like you have a bunch of nodes. There's no social network, but, once people decide about their social activity, there will be some realized, social network over which, the infection is going to spread. All right. So I'm going to, make the model more precise in the next slide. So in terms of the main results and insights, so we sort of have three main insights. So the first one is, greater testing can lead to more sort of social activity or, less social distancing, and therefore a denser social network. And then what I show is, for a range of parameters, paradoxically, greater testing can increase infection. You expect once you increase testing, it's going to decrease the infection probability. We'll see that for a range of parameters, that's not necessarily the case. And then this sort of non-monotonicity result, it has some implications in terms of the optimal testing policy. So the first thing is the optimal testing policy may leave some of the testing capacity of the society unused. You have this many tests, but you somehow find it optimal to not use all of those. This may sound strange, but what this implies or what this suggests is testing should be combined with mandatory social distancing. And once you do that, then you're going to end up using all the testing capacity, and things are going to become much more efficient. Any question about the high level idea? Okay.
Sorry. The tests are able to detect those who are asymptomatic, or the tests only detect those whose viral load is above certain threshold?
Again, so this is like a sort of the way we're going to model it is at a sort of a more abstract level that that's not going to matter that much. So the tests are just going to sort of determine the probability with which you're going to be tested once you are infected. So that's so once I introduce the model, it's going to become more clear. But whether you're asymptomatic or not, it's not going to matter that much. So I'm not going to model that in our framework. I'm not going to model asymptomatic transmission or.
But I think he wanted to ask whether the tests are perfect or not.
Very good, very good. I'm not going to assume they're perfect, but it's not going to matter for the results that I will present. So I'm going to assume that if you are infected and not tested, you're going to transmit infection with some probability. And if you are infected and tested, you still are going to transmit with some probability, because before you test positive, you may have interacted with people, but this probability is smaller than the case that you are not tested. So it's just if you're tested, you still transmit, but with a smaller probability. So this can be 0 or anything small. Only for.
But it's not that everybody will transmit. I will transmit if I got infected.
Good. So.
But you have just this general idea that everybody just wakes up and is infected with something.
No, that's not the case. So I guess that's so. Let me actually answer that question once I introduce sort of the stochastic process governing the sort of spread of the infection. So I guess I can answer that question once I introduce that. All right. And in terms of the literature, we sort of relate to the 3 branches of the literature. So one is on endogenous social network formation. So here we're going to use a sort of a simple network formation model in which probability of 2 individuals connecting with each other is just going to be proportional to the product of their social activities. So that's the sort of a network formation model we're going to use. And we also relate to the sort of literature in econ that sort of explores that precautionary tools sometimes can increase risk taking and can have adverse effects. And this has been documented in the context of hydraulic brakes and also in the context of HIV treatments. And the third sort of branch of literature that we relate to is the recent literature on epidemics in COVID-19. So pretty much all the talks in this workshop should have been listed there. So I did list a few of those and didn't have enough space to include the rest. But the list of papers we see here is by no means complete. And as you see, all of those are after 20. So that's all right. So let me jump to the model. So I'm going to consider n individuals, 1 to n. And then each individual, if I consider individual I, for instance, is going to decide about her level of social activity. So this is going to be some number xi between 0 and 1. And this is going to be probability with which you're willing to connect with others. And then there are going to be k agent types with different values for social activity. For instance, young people may have a higher value for interacting with others compared with others. So there will be k agent types with different values for social activity. But for the most of the talk, I'm just going to assume there are 2 types. low value and high value agents. And I will show you how the results are going to extend when we consider more than two types. So again, I'm going to consider two types of agents, high value and low value.
In addition to the excise.
Yes, so this is the value per social activity level. So at the end of the day, once I introduce the utility, it's going to be clear. So your sort of utility from social activity is just going to be your value times your actual social activity level. So it's going to be your VI times your XI. All right. So just a little bit of the notation. So I'm going to denote the set of high and low value agents by cal H and cal L. And then, in terms of the spread of the infection, so the virus infects a uniformly random, individual, and then spreads according to sort of a variation of the independent cascade model. So I'm going to, make that more formal. But, before that, so let me tell you about the testing policy and also the contact network. So what is a testing policy in our setting? So we're going to consider like a very simple testing policy. So the testing policy is just a pair of two probabilities, alpha L and alpha H. And those are going to be the probability with which you test low value agents and the probability with which you test high value agents. So that's what I mean by testing policy.
How do you know if an agent is inactive?
So I'm assuming you know that. So I'm assuming you do have that information. So it's you can say, based on age of people, I'm going to decide whether they're low value or high value. But, this is a full information game, so I'm going to assume that you know that. All right. So, let me tell you about the contact network, and then, based on this contact network, I can introduce the sort of the infection probability and the stochastic process for that. So what is a contact network here? So the social activity profile, this vector of x1 to xn, this is going to generate a contact network, a random contact network. So what's the probability of agent I and J being connected with each other? That's just going to be proportional, some eta, some number between 0 and 1, times the social activity of individual I, times the social activity of individual J. So that's how we define the contact network, and it depends on the sort of the social activity of the two endpoints.
Do I see the XIJs of the other people, or do I also see the, as a player in the game, do I see only the XIs, or do I also see the realized edges?
You see the XIs. You see the XIs. And then because you're making a decision ex ante, that's the only thing that will appear in your expected utility. So you don't need to sort of see the realization. You make this decision before seeing the realization, and you try to work with your sort of expected utility.
I think the way you're modeling preferences, your value for social activity is independent of how many people are participating in the social activity, right?
Yes, that's a good point. Yes. So it's not, so it's like, how often I'm going to go out. And, once I do that, I'm going to interact with others. Yes, that's a good point. So it's not a sort of a pairwise, stable kind of, model of network formation. Just like, I'm deciding, this is how often I want to go out, and that's it. So I get value for that. And, one thing, regarding to that, let's actually think about, what sort of activities, I'm capturing with this sort of model. One is, it doesn't require sort of a bilateral agreement. So, if I go out, I'm going to get social activity. And the other is, this captures activities in which, multiple individuals are going to interact with each other. For instance, you want to play basketball. You guess you can play basketball solo, but it's not going to be that fun. But, you need more than one person, to play basketball. Or, you want to go to office. You're going to, see people. You're going to a restaurant, or, you're going shopping. So it captures these sort of things, and it doesn't capture, activities like a solo activities. It doesn't capture you going for biking or hiking.
I would have thought the other way around. I would have thought that it captures, solo activities like hiking, but then, I randomly bump into somebody and they give me COVID. But, if I'm thinking about going to a party, I would enjoy that party more if more other people were also going.
So I guess we both know what is captured, but yes. So if you're thinking, if I go hiking, I get to interact with others, sure, then that is going to be captured in this model as well. But essentially, this is going to capture scenarios in which you get to interact with people. You're going out, and by doing that, you sort of interact with people. You see them with.
If nobody goes to the restaurant, I will not interact with anybody. You still give me high or low value, right? It's really it's sort of sitting in the register, imagining the other people, which is I enjoy. Not the other person, actually the people.
True. So, I'm assuming you go to restaurant to eat. So, that's your end goal. So it's like, you get value. You get value. No, you get value from going to restaurant. So that's your value for social activity. But by doing that, if others also go to that restaurant, you're going to get in contact with them. So that's how you should think about it. If I go shopping, I get some value for that. How often I want to go shopping. So I get that value exactly. So the value is you want food. You want to go to a restaurant to eat. So you get value from that. But by doing that, you sort of interact with others, or you came into close contact with others, and you may get infection from those. Yes.
Just to understand, the only externality is through infections.
Correct. Exactly. Very good. Sorry. Yes, that's actually so. The only externality is through the infection. Exactly. And that's going to sort of simplify the analysis. I will show you, how this is going to help us. Any other questions? Very good. So now that we know the sort of contact network, or the social network over which the infection is going to spread. So let's say, what is the sort of the stochastic process governing the spread of the infection. So one of the individuals, again, uniformly at random, is going to get infected, and the infection spreads to others, over this contact network by using a sort of a slight variation or extension of the independent cascade model of Kempe, Tardush, and John Kleinberg. So let me tell you what is that. So again, we have a source chosen, uniformly at random, and then an infected and not tested individuals, and therefore, not isolated, is going to, be active for one round, and it's going to transmit infection to her neighbors with some, transmission probability beta, some number between 0 and 1. Versus here, node 1, if is not, tested, is going to transmit to 2J and I as well with some probability beta. And an infected and tested individual is going to, be isolated. So here I can assume that, the transmission probability is just going to be 0. But, to allow for, more flexibility, what I'm going to assume is, before the isolation takes place, this individual is going to be active, and, with sort of a smaller probability, this individual may, infect her neighbors. So, if here node 1 is infected and tested, she's still going to infect the neighbors, but with a smaller probability.
Does she still enjoy your activity? Does she get the gamma H?
Yes. So she's still
independent of whether I'm tested or not, I will still as much enjoy one.
Yes. So
independent of whether I get tested or not, I will still get my full value of going to the supermarket.
Exactly. So, today in the morning, you're going to wake up and you're going to say, well, today I want to go, for lunch to this restaurant and for dinner to this other restaurant. So there you decide you're excited. And then at the end of the day, at night, you may, have gotten the infection. That's how we should think about it. All right. And an active individual is going to remain active for one round. So we're going to end up having a bunch of active individuals.
I'm sorry. I still want to understand. So so this morning I go out and but maybe I might want to avoid being tested, because if I'm tested, I might then you will actually have some chance that tomorrow you isolate me, and then tomorrow I can't go to the supermarket. So I really don't want to be tested because I want to go to the supermarket, maybe infected or not.
That's an excellent point. So, we'll see that, the sort of the negative term in your utility is just going to be the probability of infection. And that can include, what you're saying to some extent. But to sort of exactly capture what you're saying, we needed sort of a dynamic model. And this is not a dynamic model. So here, ex ante, I'm going to decide about my social activity level and get some utility from there. But what you're saying, requires more of a dynamic model, and then you want to see, whether people, have incentives to perhaps misreport that they've been infected or things like that. So I'm not going to consider any of those. So this is a sort of a much simpler model. Sorry.
My only choice is whether I go out or not.
Exactly, or how often? Yes, this xi, your social activity level. That's your only choice. Yes. Right. And we're going to end up having a bunch of active agents and the infection simultaneously and independently from active agents is going to transmit to each of the sort of uninfected nodes in an order independent fashion. So for instance, here, if 1 and 2 are infected, then the probability of infection getting to node J is just going to be 1 minus 1 minus beta squared. So if one of these people, for instance, 2 is tested, then this probability is just going to be smaller, 1 minus beta times 1 minus beta. So this is the stochastic process that defines the spread of the infection. So now with that, I can introduce this notation. So this is like an important notation that I will use throughout the talk. So P sub I superscript inf x, this is the sort of vector of social activity levels. This is also a function of the testing policy, alpha L and alpha H. And this is going to be the expected infection probability of individual I in the random network of contacts for social activity level X and for testing policy alpha L and alpha H. Any question about this quantity? So this is like a complicated quantity. It's not easy to sort of write this down explicitly, but we'll see that the only thing we really need is some sort of properties of this quantity. That's pretty much the only thing we need for the analysis, which hopefully will become clear throughout the talk. All right, and so let me tell you about the utility of agents. I guess I sort of talked about that a little bit. So if I look at agent I, their utility is going to have like a positive term that's going to be VI value per social activity level times her social activity level XI. And this value, remember here we're considering only 2 types. So this value is either high value or low value. So that's a positive term in the utility. This is because individuals value social interaction. And then there will be like a negative term. This is just going to be the probability of infection. And this is simply because individuals incur costs when they get infected. Then I have a third term. So this is, I could just not have that, but I guess it just makes sense to have it. So this is like a possibly small cost of getting tested, or the expected cost of getting tested. So what this third term says is, everything else equal, I prefer not to be tested. These swabs, for instance, for COVID, they're kind of painful. So everything else equal, you prefer not to be tested. Questions?
You prefer to be tested.
Yes, everything else equal.
Make sure what your situation is.
Exactly, like everything else equal. So if there is no externality whatsoever, then you just don't want to, use the swab. So that's what it says. And you can imagine this thing being small, so it has no sort of impact. Yes.
Is it easy to extend the additional types for having different risk averseness in terms of getting affected or not?
It's a good point. Like having sort of a idiosyncratic sort of coefficient here, perhaps, is that what? Yes, that is easy. So the only thing that will be important is the sort of relative weight that you assign to your social activity level and to infection probability. So it's sort of one can think about people may have different costs from getting infection, which is the case.
Even for the low value individuals, VI is positive, right? So
yes,
wouldn't they still want high activity? Wouldn't that still increase their utility?
So if they increase their social activity, yes, it's going to increase their value from that. But per social activity, they just have a lower value for increasing their social activity. So it's like this VI, think about it as the unit of social activity. So this is per social activity, and this XI is your actual social activity, which is your choice. But this VI is something inherent. Yeah, so it's just you just enjoy staying at home more than someone else. It's just this is that sort of parameter. So it's something idiosyncratic.
Yeah. There's no cost to, like, if I don't like social activity, I don't have a cost for it.
I see. So you want to have a negative term? No, I'm not going to consider that in this model. Yes, that's a discourage social interaction. So we're not going to have.
But you could introduce in your utility also things that depends on global level of infection. Because, for instance, you can care about transmitting the disease, which does not appear in your utility function.
So
here everything is agent centered. But could you have something that is more population centered as well?
Oh, very good point. Yes, I guess this goes back to like the question that Kimon asked earlier. So the externality is here. So here, your infection probability, the infection probability of individual I, this depends on the activity level of others. So if others are more socially active, so this is going to be higher. So, I incur some cost there. So it is there. So the externality does exist in this model, but it's only in this, probability of infection term and not in the first term. So it may be hard to sort of see it, but this vector, it depends on the sort of the activity level of others. So there is some externality here.
I think the question, well, okay, I understood the question differently. There's two possible PIs. One is my probability of getting infected if some random other person starts the infection. But maybe I'm a very socially conscious person and I don't want to be patient one in a global infection. So I might care about the probability of creating an epidemic.
I see. That's a good point. So sort of having the infection probability of other people, perhaps, with a smaller coefficient. So I'm not going to consider that. So whether that changes things or not, I actually don't know. So it may or may not. So I don't know. So that's something we can.
In your model, the two may be the same.
It's what?
Well, the probability, right? So since you have this independent cascade model, the probability of being infected is the probability of happening to lie in the largest cluster, more or less. And the probability of infecting others is also the probability of lying in the largest cluster. So maybe they're actually
I guess
correlated here.
Yes, so there may be some connection. Yes, of course, yes. So my probability of infection is of course related to others' probability of infection. So again, I don't know what happens if you include the infection probability of others in the utility as well. So you're saying it doesn't matter because
I don't know what you call an infection. Is that if a random person gets infected, or if it's conditioned on being a large outbreak, then of getting infected? I don't quite know what your PI is.
So this is the probability of ever getting infection in the independent cascade model.
Under the assumption that a random person is patient one.
Exactly. Initially, like a uniformly random agent is going to get infected. And your number I, your agent I, probability of you ever getting infected.
And I think in your model, the probability of me infecting a random person is exactly the same as a random person infecting me, because it's just the probabilities that they're connected in your percolation model.
Yes.
So actually, your social good is exactly the same as the egoistic one here.
I guess I don't know the answer, but I trust Christian, so I guess the answer is it's not going to matter, I guess. Yes, perfect. All right, so before telling you about the equilibrium characterization and the analysis, I told you, there are a few properties of this infection probability that is pretty much all that matters in the analysis. So let me tell you a little bit about those properties. So the first one is monotonicity in action profile. So that simply says, higher social activity means a higher infection probability. So that's the sort of the first property that this quantity has, and we are going to require. So the second one is concavity in action profile. So what that says is, if I'm agent I, my infection probability is going to be concave in my social activity level. Or in other words, the marginal increase in the infection probability is going to decrease as the social activity increases. So that's something we prove holds for our process, and it kind of makes sense to sort of expect that thing to happen. The third property is monotonicity in testing probability. So all that says is, simply as I increase testing probabilities, the infection probability is going to decrease, something that we would, naturally expect. And my claim is, these three properties are the main properties that, I'm going to use in the analysis. So if you don't like, the stochastic process I, introduced here, as long as whatever probability of infection you have satisfies these three properties, then the rest of the analysis is going to go through. All right, so let me actually highlight this sort of last bullet here, monotonicity in testing probability. So what that says is, for the same action profile, if I test more, the infection probability is going to decrease. So let me write that here. For an exogenous social activity profile, increasing the testing probability decreases the infection probability. Now, the sort of question we're going after is, how about in equilibrium when individuals choose their social activity endogenously? So can we have the same thing, or something else can happen there? But in order to answer this question, we do need to characterize the equilibrium, right? So we do need to characterize the equilibrium social activity of agents. So let's actually work toward that. So in terms of the solution concepts, I'm going to consider symmetric equilibrium, where the action of each agent depends on her position in the network, her type, but not on her index. And this is something that is going to simplify the analysis. And in the paper, we do consider asymmetric equilibrium as well. The results are very similar. Sorry, there's a question. Yes.
Thank you. Just to understand, if you only had one type of agents, wouldn't you get the same answer, right? Where we only have one action, symmetric equilibrium.
Correct. So yes, so this sort of non-monotonicity that I was talking about, you still get it with one type, but I think the results for two types is just more interesting. So that's why I chose two types. So you can have the sort of the non-monotonicity for any integer k, and I chose 2. That's the bare minimum. Yes, but k is the bare minimum that makes things more interesting. Yeah, but yes, your intuition is definitely right. That with k1, with one type, you sort of get the same non-monotonicity result. That is true. All right, and then if I look at the utility of each agent, that's going to be convex in her social activity level, because it has a linear term minus a concave term. So what that implies is the equilibrium is going to be either 0, 1, or a mix between these two. So we should look at equilibria that belong to that class. But let's just start with the simplest one. So I'm going to ask, when is social activity 1 for both high value and low value agents an equilibrium in this case? So let's see whether we can answer this question. To answer this question, I'm simply going to evaluate the utility of agents when they're playing 1, and the utility of agents when they're playing 1 and one of them deviates to 0. So the left-hand side, if I'm agent I, if I'm playing 1, I'm going to get value vi, and I'm going to get this probability of infection. So this is high value agents are playing 1, low value agents are playing 1, and the testing policy is alpha L and alpha H. If I deviate as agent I and play 0, so what's going to be my utility? So I'm not going to get any value from social interactions. And because my xi essentially is 0, I'm isolated in this network. So the only chance for me to get the infection is, when I'm the source of the infection. So the probability of getting infected is just going to be 1 over n.
How do you know that an equilibrium exists? If it's 0, 1, it could be I'm playing 0, then you want to play 1, then I will want to play 0. So far you only have argued to me that my best response is 0 or 1, not that this is an equilibrium.
Very good. So this is going to sort of show that, if this thing holds for all I, then this is going to be equilibrium. But I guess your question is deeper, is like, what if there are other equilibria as well? Yeah, that's a possibility. And what I will argue, well, I'm not going to have it on the slides, but in the paper we show that these are the sort of unique equilibria you will end up having. So I'm going to characterize the unique equilibria here. So you're not worried about other perhaps non-intuitive equilibria existing as well. All right, as you said, if this thing holds for all I, and here because we have 2 types only, if this thing holds for a low type agent and a high type agent, then we can say for this region, for alpha L and alpha H, for testing policy belonging to this set A1, the sort of social activity of O1, both agents being fully active, that's going to be an equilibrium. So that's easy to see. But now let's see, what happens if I sort of decrease this testing probability or this testing policy. So if I decrease the testing policy, these alpha L and alpha H, this probability of infection is going to increase. And at some point, I will end up violating this constraint. So I will step outside of this set. So which one is going to be violated first? I mean, it's easy to see that the constraint corresponding to low value agents is going to be violated first. And then one can argue that there is no symmetric pure equilibrium there. Going back to Christian question, so one can argue that there is no symmetric pure equilibrium there. So, one needs to look at mixed strategy equilibrium. So now let's look at that. So what's a sort of a candidate for a mixed strategy equilibrium? So let's consider this symmetric equilibrium. Low value agents are going to play mixed, and the high value agents are going to play fully active, are going to play 1. So let's see when we can have such equilibrium. My claim is, in this other set A2, which is disjoint from the previous set, we're going to have such equilibrium. So let's look at this first constraint here. So what does it say? So this is essentially the constraint we had in the other set A1, but with the opposite direction. So this is the constraint that is violated. And if I look at the second inequality here, so what this says is the infection probability of a low type agent when others, other high values are playing 1, I, as a low value agent, I'm playing 1 as well. And the rest of the low value agents are playing 0. So this infection probability is less than VL plus 1 over n. So it's the opposite direction of this. So those are the constraints I need, in terms of the infection probability of a low value agent. And then there is another constraint for the infection probability of high value agent. And I'm saying, with these constraints, or in this set A2, there exists a mixed strategy equilibrium, and that's going to be unique. So let's see whether we can prove that. So, how can I argue that there exists a sort of a mixed strategy equilibrium for low value agents? So all I need to do is to look at their utility when they're playing 1 and others are playing mixed, and their utility when they're playing 0 and others are playing mixed, and equate these two. So if I'm a low value agent and I'm playing 1, this is my value. This is my infection probability. High value agents are playing 1. I'm playing 1 as a low value agent. And the rest of the low value agents are playing a mixed strategy. With this gamma L, with probability gamma L, they're playing 1. With probability 1 minus gamma L, they're playing 0. And this gamma L, it's a function of the testing policy. And if I play 0, then we have already argued that my utility is going to be minus 1 over n. And to show that an equilibrium exists here, all I need to do is to sort of prove that there is a fixed point for this equation here. There exists this gamma L here. So how can we see that? So my claim is the fact that this gamma L exists, it just follows from these two inequalities and mean value theorem and sort of the monotonicity of the infection probability in the social activity levels. So what did we just prove? So we proved that in this other set A2, there exists a sort of equilibrium in which high value agents are going to play one and low value agents are going to play a mixed strategy. What's the probability of mixing? It's this gamma L that we see, solution of this fixed point equation. Yes.
Why would the mixed strategies rather than just
very good.
Continuous game, right?
Very good. Yes. So you can see that there is no sort of pure equilibrium in this set. So I guess actually I can answer your question in the next slide. So if that's fine. So one thing before that, so I just want to highlight, this infection probability, it's a complicated object, and finding this fixed point is also complicated, or characterizing this gamma L function is complicated. But the good thing is we only need the fact that it exists, and later I will show a sort of a monotonicity result for that as well. And that's the only thing we're going to need. And going back to Elon's question, so let me tell you the full characterization, and then hopefully that's going to answer your question as well. So there exists functions gamma L and gamma H in 4 regions, and the reason we have 4 is because we have 2 types. So if we had k types, we would end up having 2 k regions, such that here is the equilibrium action. So here on the y-axis, I have alpha H, probability of testing high-value agents. On the y-axis, alpha L, probability of testing low-value agents. And I'm going to tell you what is the equilibrium action of high-value and low-value agents. So if I'm in this region A1, then full activity for both agents, for high and low, 1, 1, that's going to be the sort of a unique equilibrium there. If I go to this set A2, we can prove that there exists no pure strategy equilibria there. So one needs to look at, sort of mixed strategy equilibrium. And what is the mixed strategy equilibria? High value agents are going to play 1, and low value agents are going to, mix with this probability gamma L.
So I just have an understanding question. You have an X which you choose between 0 and 1. Is there a difference between playing 1 with probability P and 0 with probability 1 minus P, or playing strategy P?
Yes, there is a difference. Yes.
So, and you really mean mixed here, right? So because I could.
Yes, that's a good point. So, you remember that I told you that the utility of each agent is convex, and therefore, your best response belongs to one of the extremes. So, it's either 0 or 1, or a mix between those two. And
I see, which is different from the value in the middle, which is actually definitely worse.
Very good. Yes, it's different than playing something intermediate. All right. And as I keep sort of decreasing the infection probability, or sorry, like the testing probability, and I will get to this region A3. In that region, the equilibrium, or the unique equilibrium, is going to be high value agents playing 1 and low value agents playing 0. If I keep decreasing the testing probability, I will get to a region in which high value agents are playing mixed with some other function gamma H, and low value agents are going to play 0. So that's the sort of the characterization of the equilibrium we have. All right, so now let's actually see what is the impact of testing policy on the infection probability. So I'm going to start with the simplest case, in this region A1. So in this region A1, full activity level for both agent types is going to be an equilibrium. So now, if I increase the testing probability, the infection probability is going to decrease, right? So if I'm within this region, the action profile is just fully active for both types. If I increase testing, infection probability is going down. Nothing surprising happens there. Now let's look at what happens in region 2. So in this region 2, the infection probability of low value agents, one can use this fixed point equation to show that it's going to be proportional to this gamma L function that I introduced earlier. So again, the infection probability of low value agents in this region A2 is going to be proportional to this gamma L function, which is the solution of this fixed point equation that we saw earlier. And my claim is this gamma L function, and therefore the infection probability of low value agents, is going to be increasing in the testing probability. And that's a sort of the paradoxical result that I was going after. This gamma L function, and therefore the infection probability of low value agents, is going to be increasing in the testing probability. So let's see, how we can prove this. I have a sort of 2-line proof of this, or 4-line proof of this. So how can we say this? So let's suppose the contrary, alpha prime is higher than alpha, and gamma L at alpha prime is smaller. And I'm going to get to a contradiction. So let's look at these equations. 3, right? You're right. So I was counting the top line as well. All right. So the first equation. So where does that come from? So that's just the definition of gamma L. So it's just this fixed point equation, right? So I have alpha as a testing policy, and gamma L at alpha. So it's just the definition of this fixed point. Now let's look at the first inequality. So where does that come from? So gamma L prime is smaller. So I'm sort of decreasing the social activity level. So the infection probability is going to decrease. So now let's look at this other inequality here. So where does that come from? So I'm keeping the social activity levels the same, but I'm increasing testing probabilities. So again, the monotonicity of the infection probability in the testing policy, in the testing probability, this is going to decrease, right? And the last equality is again the definition of gamma L, this time evaluated at alpha prime. This is just the fixed point equation that we had, and this is already a contradiction, showing that the infection probability of low value agents in this region, as I increase testing, the infection probability is going to go up surprisingly. And one can argue the same thing for region 3 and region 4. So let me put all of this together. So higher testing in the first region, A1, is going to decrease the infection probability for both types. So nothing surprising happens there. In region 2, higher testing is going to increase the infection probability of low value agents, and is going to have no impact on the infection probability of high value agents. Something paradoxically happens there. Again, in the third region, by increasing testing, the infection probability decreases. So nothing surprising there. But again, in region 4, increasing the testing probability is going to sort of increase the infection probability of high value agents. So sort of the takeaway message here is greater testing increases the infection probability in regions A2 and A4 that we have sort of mixed strategy equilibrium. So whenever we have that, then by increasing testing, we're going to end up increasing the infection probability. All right, so let me illustrate this result in this picture. So I'm going to look at this region A4. So let's see if we can get some intuition to this sort of non-monotonicity result. So what happens in this region 4? So low value agents are going to play 0. So the infection probability is essentially 0, or 1/n. High value agents, this is going to be their sort of infection probability. High value agents are playing mixed. But as I increase the testing probability, as I increase alpha here in this picture, I'm creating some incentive for those people to go to full activity. I'm increasing testing. I'm creating some incentive for those people to go to full activity. But one thing that I argued is there is no pure strategy equilibrium in this region. While I'm still in this region, there is no pure strategy equilibrium. So what happens is in equilibrium, the incentives for mixing is restored by increasing the infection probability. So that's a sort of the intuition to keep in mind. And then as I further sort of increase the testing probability, high value agents are going to start playing full activity. The infection probability decreases there, nothing surprising there. But if I further increase that, now low value agents start playing sort of mixed strategy. And by increasing the testing probability, I'm going to increase the infection probability of low value agents. So again, something sort of paradoxically happens there as well. Any question about this? Yes.
This will be a naive question because I don't really speak econ, but this slide helped me a lot. So I guess the intuition behind why this paradoxical behavior arises, is it correct to say that as testing increases, because you have full information and you kind of know the overall environmental risk is dropping, it incentivizes you more, right? So
yes, that is right. Yes,
I see.
Yes,
and does that, if you had more of a myopic strategy, do you expect something would similarly happen, or is this really from the global information?
No, this is coming from this. Yes, so to see this sort of non-monotonicity, you do need to sort of have people who are strategically, deciding about their social activity. So you do need that sort of behavior to get this sort of results. That's a good point. Yes. All right. So I did characterize the equilibrium for k equal to 2 types. So I have a picture to tell you what happens with 3 types, but I guess I don't have enough time to go over that. But just to tell you, what happens in general for k types, we can still characterize the equilibrium. Instead of having 4 region, we're going to have 2k region, and we still get this sort of non-monotonicity result whenever we have a mixed strategy equilibrium. All right, so I would be happy to talk about this offline. All right, so far we have argued that increasing the testing capacity may increase the infection probability of individuals when we consider their strategic social distancing behavior. Now, the next sort of natural question is, what are the implications of this non-monotonicity result for the optimal testing policy? So let's try to answer this question. So first of all, what do I mean by optimal testing policy? So I'm going to assume that there is a sort of a limited testing capacity. So there are theta n tests that I can allocate to this population. I'm going to sort of refer to this theta as the testing capacity. And I want to see what would be the optimal choice of alpha L and alpha H. So here's a constraint that I need to respect. Alpha H, probability of testing high value agents, alpha L, probability of testing low value agents, the sum of these two, it has to be less than theta. So that's a constraint I'm going to have when I'm deciding about the optimal testing policy. So what's the objective? So the objective is going to be social welfare. It's going to be the sum of the utilities of all agents. And I'm simply going to maximize this. And there's a game here. So there's a sort of a 2-stage stack of a game going on here. So the social planner is going to choose the testing policy. And given the testing policy, the unique symmetric equilibrium will be played. So this, social activity levels are the choices of the individuals in equilibrium. So, there's a sort of a 2-stage game going on here. And the social planner's problem is going to be, maximizing over the testing policy, the social welfare, subject to these 2 constraints.
Don't care about whether many people get. You don't care about the epidemic.
Very good. So I'm taking like a utilitarian welfare here. So yes, so one can, think about sort of a more refined objective here. So the objective I'm considering here is the sum of the utilities of the individuals in the society.
But the probability of infection?
It is there. Yes, the probability is there. So like the probability of infection is already in this utility. So, but, one can, weight these, probabilities differently. I'm not going to do that. So I'm just going to simply take the sum of these utilities. Yes.
How much?
Can you bring the mic?
How much?
I could, in principle, put a proportionality constant in front of one or 2 terms, the positive from social activities, the negative from the probability. Mm-hmm. How much do your results depend on this?
Good. So you want to look at the sort of separate the value from social infractions and the sort of the cost of the infection probabilities, and then put different weights on those, right?
Yes.
So the results are going to be the same, similar. So it's not exactly the same, but it's like the sort of intuition that we see that, I will show you in the next slide is going to be the same. Right. So let's see, what is the sort of optimal testing policy here? I guess I'm running out of, so do I have like 4 minutes to finish? Okay. So there are 3 thresholds such that, here is the sort of the characterization of the optimal testing policy. So if we have enough tests, then, it will be optimal to test all agents. And, we're going to end up fully utilizing all the tests. If we have, some intermediary value for the number of tests, then we want to sort of discourage social activity from low value agents, and we end up underutilizing the testing capacity. And again, we get to this other region in which, low value agents are going to be, inactive themselves. So there, I'm going to fully utilize the testing capacity. And, if the testing capacity is like very small in this sort of yellow region, I will end up again underutilizing the sort of testing capacity. So the key sort of takeaway from this result is the optimal testing policy does not necessarily use all tests. So, you may as well, find it optimal to not use some of the tests that you have. And, naturally what this suggests is, perhaps testing should be combined with social distancing, right? So this sort of suggests, perhaps, that's where you can gain, you put some restriction in terms of the social distancing, and perhaps you can end up, using all the tests and do better. So let's see, whether we can sort of formalize that idea within the context of our model. So how am I going to think about social distancing here, or mandatory social distancing here? So I'm just going to put an upper bound on the social activity level of individuals. So I'm going to have an upper bound for the high value agents and an upper bound for the low value agents. And the rest of the optimization is the same. One can easily show that, for any testing capacity, there exists a testing policy with mandatory social distancing that achieves the social welfare of the first phase. So, this is sort of the best thing you can hope for. And, in this policy, the social planner is going to end up using the entire, testing capacity. So the bottom line here is, once you combine social distancing with testing, then you end up using all the tests, and you're going to do, much better than, the case in which you only use testing. All right, so that's all I want to talk about. So I'm gonna stop here, and thank you. I would be more than happy to take any questions.
Thank you very much. So Abba has a question.
Okay. Thank you. That's a fantastic talk. I like it. So by social distancing, are you talking about isolation, self-isolation, or maintaining 6 feet distance from somebody?
Very good. So that's a good point. How are we going to enforce these things? So for our model, this is something very simple. I'm just going to put a cap on the social activity level you can take. You can. This is how much you can get out of your house or something like that. So I'm just going to put a cap on your social activity level. So that's
not distance, not measuring the distance.
No. It's more like social. It's more like restrictions, I guess. It's more like
fair enough.
Yeah.
I really enjoyed that talk. Thank you. So I was just thinking that it might also be interesting to study a model in which testing decisions are also endogenous, where people are deciding whether or not to get tested. I don't know if it would make a difference here, but I think I didn't follow the discussion before, but apparently maybe your model is going to go through whether people have social preferences or not, but when interesting things might happen if you endogenize testing.
Yeah, that's a great question. I think this goes back to like the question Christian asked earlier as well. If you make that a decision, then there may be some incentives to sort of lie about the results of the testing, or perhaps not test because you think that you may have gotten the infection. There may be things like that as well. So I don't know, how that's going to change the model. Or the analysis, actually. Yeah, I don't know. But yeah, I agree with you that would be like a very interesting direction to explore.
Yeah, actually, it's very related point. So basically, if there is mandatory social distancing, then people wouldn't get tested if the testing decision is whether to be tested or not is a voluntary decision.
Right. Yeah. So yeah, again, I don't quite know the answer, but yeah, I do agree that's just a great question. So so basically, like your decision is not only about your level of social activity, but also how often you want to get tested. I guess that can be a choice. How is that going to change the result? I actually don't know. So it requires I need more time to think about how is that going to change the result. But I agree that that's a great question. So we can discuss that.
If you add mandatory social distancing, okay, I understand that you use all the, but does it mean also that you increase the optimum, or?
Yes. So you get to the first phase, which is basically you're maximizing the welfare without the equilibrium constraint. So as if you don't need any coordination among people. So you kill one of the constraints, so you get to a higher objective. That is right. Yes, that is exactly correct. Yes.
Okay, so I suggest that we thank our speaker again, and we can ask further questions for the break.
Thank you. Thank you so much.